So here we are with lesson 2.1.1, the first lesson in chapter 2. The unit essential question is, how do we find area under the curve? Lesson essential question for this and a few other lessons will be, how can function transformations be applied to piecewise functions? You can certainly read a little bit there about piecewise functions. The basic summary there would be that when we're graphing piecewise functions, which you should have experience with from Algebra 2, we are only graphing sections of functions over a defined domain. So, in the math notes box there, it tells us a little bit about that, saying that, we'll graph this line when x is less than 3, and we'll graph this parabola when x is greater than or equal to 3. So we're just graphing a section of each of those families for one combined graph. So when we're talking about f of x, we're talking about both these lines considered simultaneous. However, those f of x is made up of a linear and a quadratic. So we're going to get some experience here graphing our own. Let f of x, this is problem 2-1, let f of x be represented by x squared plus 2 when x is less than or equal to 2, and by 1/2 x plus 1 when x is greater than 2. So we should be graphing experts by this point in our math career. I would expect that the x squared plus 2 when x is less than or equal to 2 is something we can graph freehand with no tables or calculators or what have you, but I suppose that some of you may still be in that place. So x squared plus 2 typically would be a parabola shifted up 2. But we're only talking about when x is less than or equal to 2. So we're going to plot points starting at 2 and to the left of 2. All right, and that's a closed-in circle at 2. Now, how am I generating these points? Well, I moved my parabola up 2 because that's the vertical shift. Okay. And then I know how to graph a parabola over 1 up 1 because 1 squared is 1, over 2 up 4 because 2 squared is 4. I'm only going to graph the section that is less than or equal to 2. So that would be to the left. Less than is left. Then the second part of my graph is made up of a linear function, 1/2 x plus 1. Again, I'm going to use graphing shortcuts. Up 1, all right, would be my y-intercept, and then up 1 over 2 is my slope, rise over run. That's an open circle at the x value of 2. Up 1 over 2 from there to generate the remaining points of my line, and I draw that section of the function like that. So again, the reason why this sort of break in the graph here happens at 2 is because that is the sort of focus point of my domain, which would be 2. That's why the parabola only is to the left of 2 and the line is only to the right of 2. Problem 2-2, let us look at an application of a piecewise function. Lisa makes $4 an hour babysitting before midnight, $6 an hour after midnight. She begins her job at 7 p.m. Complete the table, the money amount shown. Here, it's $4 an hour until midnight. So let's see here, if hours of babysitting, she starts at 7, so that's term 0, so that means this is the first term. So after the first hour, she has $4. After the second hour, she has $8. After the third hour, she has $12. All right. The fourth hour would happen at 11. I'm not sure why they have 11:30 in here. At 11 will be the fourth hour, and she would have $16. And it says here before midnight, and $6 an hour after midnight. So we'll go up into midnight, and we'll say that's 20. Now after midnight, she's going to be making $6 an hour, so at 1 a.m. we'll jump to 26, and at 2 a.m. we would jump to 32. So you'll notice here the growth is up 4, okay, until this point, and then the growth changes to up 6. Okay, so part B says if we wanted to fill out the entries after midnight in the table below, we need to realize that it's a piecewise function, therefore our slope is changing after that 5th hour. So they already sort of set up the domain for us here. We would need to set up the equation. The first equation would be just 4x, because it's $4 per hour, and there is no starting value. She didn't come in with any money. So plus 0, but you don't have to write that. Now the second equation, here's where some people get a little goofed up. It's 6x, because it's growing by 6. However, she has money now. By the time she gets to midnight, she already has so much money. How much money does she have at midnight? She has $20. So 20 would be our starting value there. And again, they already have the domain written for us. And if you didn't know that ahead of time, the way you would get that 20 without the table would be to take this equation, plug in your endpoint, which is 5. 5 times 4 is 20. That tells you your starting point for the next equation. Here's another piecewise function. Another way to graph piecewise functions would be to use a table of values, which is still something that should be within our realm of possibility, especially for someone who maybe still struggles with some of those graphing shortcuts. So let's see here. I'm trying to put this behind something, whatever. Okay. So we could just fill in a table. So x squared plus 2. This is similar to the original one we did when x is less than 1. So we start at 1 as our starting value, plug that in, and we get values for our table rather than, using graphing shortcuts. Okay, so, it's all in what you prefer. Okay, however many points you need to better graph a parabola, you just go ahead and fill that table in. And then for when x is greater than 1, again, we're starting at 1, even though we know it's going to be an open circle. This one over here is a closed-in circle because of the equal to. We still start at 1. So 2 times 1 is 2, plus 7 is 9. 2 times 2 is 4, plus 7 is 11, and it's growing by 2 each time, so the table is easy to fill in. Okay, now if we were talking about graphing that, sorry, my graph here, I can't get it to be, sort of on top of the page, so we'll just graph it from this point, 1 less than or equal to 1. So here you would just plot your points over 1 up 3, over 0 up 2, over 1 up 3, so forth. Graph that parabola. That parabola looks very similar to the one we already graphed because it's almost the same except it's starting at 1 instead of 2. Then you graph that second section of your line here where we go over 1 up 9. Okay, and my slope is still 2, so I'm going up 2 over 1 there, so it's going to be a much steeper slope. Same idea. 2-4 is using your graphing calculator to do that. So if you have a graphing calculator at home, it's very simple to graph a piecewise function. You type both equations into y1, except we put our equations in parentheses and we define our domain right afterwards. You can find your inequality symbols on your graphing calculator under second test, and that will bring up your inequality symbols. And then when you graph that, you'll get that piecewise function. Now, again, the problems that we found with asymptotes, remember when we graphed hyperbolas in Algebra 1, the calculator would always draw in the asymptote, even though, when we graph it by hand, we use a dotted line to represent that, or technically speaking, there is no line there because it's undefined. Same thing works for these piecewise functions. You'll notice that that piecewise function that's supposed to be a parabola and a line appears to be connected because, again, the same reasons that the TI-83 was, one of the first of its kind. It's the same reason why in this situation we get the same result as the hyperbola. So just remember, though, that this would be a missing sort of section of that line. Here's some math notes on piecewise functions and the definition of continuity. Now, we're not going to define continuity till chapter 5 when we start talking about limits. For now, though, we can define a continuous function as a function that we can draw without lifting our pencil. So both of these here would be continuous functions. However, that first piecewise function that we graphed that looked like that would not be continuous because you could not draw that function without lifting your pencil in this area here. Last, we have one more piecewise function here to graph, 2 to the power of x when x is less than or equal to 2, and then negative 2x plus 9 when x is greater than 2. Same idea, and you can plug these in your head. So I'm still starting at 2, plug that in, I get 4 over 2 up 4. All right, and then I'm going to the left because it's less than, so 1, 2, 0, 1, and that's an exponential. Remember that that has an HA. And then we have negative 2x plus 9, all right, when x is greater than 2. So plug in 2 there. 2 times negative 2 is negative 4, plus 9 is 5. So that line, or that point's going to be 1 above there, and it's going down 2 and over 1. And I draw that section of the line. Find the domain and range of the function. Well, domain is all real numbers. All right, you could also say the domain is negative infinity to infinity. Okay, all x, I guess. You can see it written. Okay, because there is no break left to right in that function. Now, range sometimes gets a little tricky. Remember, going lowest to highest. So the lowest this graph goes, some people get confused here because this section of the graph will never go below 0. However, we're considering the whole function g of x, and this line goes way below 0. It actually goes forever below 0. So the lowest our graph can go is negative infinity to y. To the highest our graph can go, y value would be 5, not included because it's an open circle. So that's one way you could write it. You could say all real numbers less than 5. And again, the idea here is we're considering the whole function, so both parts at the same time. Yes, I understand there's a little gap here between those. So some people might say, well, what about between 4 and 5? Well, this section of the line takes care of between 4 and 5. It's covered. And that's it for today.